So we've got some implementation details to cover with Dijkstra's algorithm. We'll start thinking about data structures and things that can be used to optimize this. But first, we need to spend a little bit of time thinking about why Dijkstra is correct. So I danced around this a little bit as I was going through the algorithm walkthrough on the example problem. But it would be really useful at this point to focus right in on a single step of the algorithm and show exactly why that step was the right thing to do. Okay, so why is Dijkstra correct? So what we're going to do is we're going to focus on the algorithm right after we added C to the tree. So it's kind of obvious why C needs to be added to the tree, right? Why C, why you've got to have one connection to A that's just a single node, right? There's going to be one shortest path from somewhere to A that's just, one link, and it's clearly C in this problem, right? That's something that I shouldn't have to argue too hard about. But what's less obvious is why it's the right thing to do to add B in the second step. So to discuss this, I find it's really useful to delete everything that the algorithm hasn't explored yet. So far, what does the algorithm know at this stage? Well, all it knows is that it has added some stuff to the tree and that there's two nodes that are adjacent to the tree. Okay, so now that we know what the algorithm knows, let's think about what kind of these things mean. Okay, so what is the tree? Right? If I say the algorithm knows this tree, what am I actually trying to express? Well, what I'm trying to say is that the algorithm knows the shortest paths from A to A and the shortest path from C to A. Okay, so the tree is a list of shortest paths. Okay, this is a list of shortest paths. And now I didn't focus on it too much as I was going through the run-through, but another fact is that at each point in the algorithm, what we need to do is write the distance. As soon as we add a node to the tree, we need to write the distance from that node to A, down on that node, right? And so now let's think about given the fact that everything that's highlighted in red is part of a shortest path or expresses a shortest path, let's think about why it is the right thing to do to add B. Okay, so let's think about what the shortest path from B to A must look like. Okay, so there is one shortest path that's written. Okay, so the fact that B is adjacent to the tree means that there is an edge connecting B to something in the tree, and that something in the tree is part of a shortest path to A. Okay, so one kind of candidate shortest path from B to A goes directly through the tree. Okay, so let's write a list of kind of possibilities for the shortest path from B to A. Okay, so here are the possibilities of shortest paths from B to A. Okay, so the first possibility is that it goes through the edge that we've already written down, right? It connects directly to the tree, and then from wherever it connects in the tree onward to A. So kind of possibility one is through, and I'll say B's connection to the tree. To tree. Okay, so that's one possibility. And what is this? Well, that's let's color code a little bit. That's this edge right here. Okay, so that's one of the possibilities. So there's one other possibility. Okay, so you look at this and you say, well, I guess there's a whole bunch of edges. There could be a whole bunch of edges back there. Why is there only one possibility? Well, the only other possibility is that it connects through the tree, it connects to the tree through some other node that is adjacent to the tree. Okay, so the only other possibility, which I'll do in green, hopefully it's distinct enough from the blue, the only other possibility is that it connects through E's connection to the tree. Okay, so the other possibility is through E's connection to the tree. Okay, and why is that? Well, because E is the only other thing that's adjacent to the tree. If there were other things that were adjacent to the tree, B could connect through them as well, right? But let's just focus on the problem at hand for now. So the other possibility is that B connects somehow, right, somehow or other, through maybe some other network of nodes, and then to E, and then from E to the tree, right? So it could go like this. Okay, and so this is the other. There we go, dotted. That's how we'll distinguish it. This is the other possibility. Okay, so we can ask, what's the cost of a connection from B directly to the tree? Well, that cost is just exactly 2. Okay, what is the cost? Alternatively, what is the cost of B connecting through E and then to A? Well, it is the cost of going from E to A plus something else, right? So I don't know what the cost of this is. I have no idea what the cost of this is, but I know that it's not negative, right? I know that it has some cost. Maybe it's even 0, right? Maybe there's a free path from B to E. But even if there is a free path from B to E, then to get from B to A through E, I still have to pay whatever cost I would have to pay from E. Okay, so either, and let me scroll over just a bit, right? So let's think about what the costs of these are. Costs. So the cost of this one is 2, right? That's just the cost of B's connection to the tree, or to A through the tree, through its direct connection to the tree. Or the cost could be 4 plus something. Okay, and what is this 4 plus something? Well, the 4 is just the cost of, I should say, the minimum known cost, min known cost of E to A, plus the cost of B to E, right? Not going through the tree. So this is the cost of B to E. Okay. And so which cost is lower? Well, the cost where B connects directly to the tree. And so that's why B is the right thing to add, right? Because there are only these are the only ways I can add a node to the tree, right, to my tree of shortest paths. There aren't any other nodes connected to the tree, right? So if I want to augment my list of shortest paths by one of these paths has to be the shortest, right? And so then we say, well, the one with the shortest path, the shortest distance front to A via the tree that we see right here has to be an actual shortest path, because there's one option right here, right? One option is to go directly, and the other option would be to visit something else that hasn't been explored yet. But no matter what we explore, no matter what we do over in that green dotted patch over there, eventually we're going to have to connect to the tree somewhere, and every other connection to the tree is going to result in a longer path than if B just connected to the tree directly right here. So that's the kind of the relatively informal reason why Dijkstra's algorithm is correct. And we can generalize this, and we'll generalize it in some ways a bit when we do Prim's algorithm in the next set of videos. But that's the basic idea, is that Dijkstra's algorithm is correct because we can say any other path other than the one that connects directly to the tree would have to have a higher cost, a strictly higher cost, which is why we say let's list all the nodes and how far they are from A through the tree, and then pick the smallest one, because that smallest one has to express a shortest path.